When people hear safety manager, they picture a clipboard cop, someone whose only job is walking the floor and scolding people for forgetting safety glasses. But in modern industry, the role looks a lot more like a systems engineer. They are high-level architects who have to balance operational speed with human limitations to build environments where injuries are physically difficult to achieve. They build their defense using a few different tools. The first is enforcement, using strict rules and fines to keep people in line. The second is the psychological approach, which focuses on training and behavior. Both are necessary, but they are fragile because humans eventually make mistakes. That brings us to the most robust tool, engineering controls. Instead of asking someone to be careful around a hazard, this strategy physically alters the environment to remove or block the danger entirely. Real industrial safety doesn't come from reminding workers to do the right thing. It comes from systematically deploying these tools so that hazards never reach the point of an injury. To build those physical defenses out in the field, we must step into the office. The foundation of safety is rigorous statistical data. This government document is the OSHA Form 300, a mandatory log for workplace injuries. By isolating columns H and I, managers track the DART rate, days away, restricted, or transferred. This counts when injured employees are forced onto restricted, lighter duty. Tracking these restricted workdays is absolutely crucial. It forces managers to recognize the true, holistic degradation of their workforce's productivity over time. This data dictates which regulatory rulebook to follow. Think of horizontal standards as the universal laws of the road that every factory must follow, from commercial bakeries to heavy steel mills and everything in between. Then there are vertical standards, which are highly specialized instructions designed for the unique dangers of a single industry, like the high-voltage risks found only in power plants. The patterns found in these office spreadsheets determine exactly which standard needs to be deployed to fix physical problems out on the floor. Out on an active construction site, the primary danger is the environment itself. It is temporary, chaotic, and constantly changing. Take a basic trench, for example. Digging a deep hole in the ground creates immense hydrostatic pressure, invisible forces from the earth that can trigger a sudden, fatal cave-in. A behavioral approach would be to tell workers to stay back from the edge. The robust engineering solution is to drop in heavy steel trench boxes to physically shore up the walls and block the soil. Above ground, the chaotic, unpaved terrain introduces severe crushing risks from heavy, moving vehicles. To manage this, engineers rely on specific vertical standards, automatic backup alarms to warn pedestrians, and heavy steel roll bar cages, called ROPs, to protect operators if their tractor tips over. And when facing the severe risks of working at high elevations, engineers demand strict controls, like 42-inch guardrails and heavy safety nets. This is a standard validated back in the 1930s, when nets saved dozens of lives during the treacherous construction of the Golden Gate Bridge. When the environment around you is completely unpredictable, passive engineering controls are the only reliable defense against sudden shifts. Inside a permanent factory, the focus shifts. Instead of dodging moving kinetic machinery, we have to manage invisible atmospheric dangers. One of the most hazardous tasks is entering a confined space. Imagine a worker climbing inside a massive empty chemical tank to scrub it clean. The primary danger here isn't a spinning blade or a falling game. It's the atmosphere itself. Heavy, toxic vapors can quickly pool at the bottom of the enclosed space, rapidly pushing out the breathable oxygen. You might assume that simply turning off the pipe valve leading into the tank is enough protection, but it isn't. High pressure can force liquid or gas to bleed right through a closed valve while a worker is inside. To achieve absolute physical isolation, engineers use a method called blinding, which inserts a solid steel plate into the pipe to block the flow, or they use a double block and bleed system. This closes 2 valves in a row and opens a small vent in the middle to safely bleed off any leaking pressure before it reaches the tank. In a factory, the deadliest hazards are usually the ones you cannot see, which means keeping workers safe requires fail-safe mechanical isolation rather than just posting a warning sign. In any operation, attempting to eliminate every single hazard indiscriminately is both physically and economically impossible. True safety leaders operate on a reasonable objective. They triage risks, carefully directing their limited resources toward hazards that are both highly dangerous and physically possible to correct. Asking workers to simply be careful, to never trip, or to lift a heavy box perfectly every single time will inevitably fail. Engineering the physical environment to adapt to human limitations is the only reliable path. Safety professionals visualize this using the Swiss cheese theory. Think of every defense, management rules, safety glasses, machine guards, as a slice of Swiss cheese. A loss incident only happens when the latent flaws and physical hazards perfectly align through the holes in every layer of defense. Fines a lost production are expensive, but when a hazard breaches the point of irreversibility, the human cost is permanent. Modern industrial safety bridges the gap between the brutal physics of machinery and the reality of human error. By building proactive, meticulously designed systems, we ensure true corporate sustainability and get everyone home at the end of the day.